Dear students, good morning to one and all persons who are here. Today we are going to discuss about introduction to medical image processing. First, let us move into the course outline. First, we are going to discuss about introduction to digital image processing. Then we are going to discuss about applications of digital image processing. Then the definition for medical imaging. Then we moved into the different types of imaging modalities. Then the principles and operations of magnetic resonance imaging, this was called MRI. Then finally, we conclude with the advantage of digital processing for medical applications. First, let us move into the introduction. The field of digital image processing refers to the processing digital images by means of digital computer. The digital image composed of the finite number of elements which have a particular location and value, and these elements are called as pixels. Digital image is a two-dimensional array of pixels where the size or resolution of an image is defined by width and height, where width is given by n pixels and height is given by m pixels. Also, the other parameter is the precision of pixels, that is given by 2 power n amplitude level, where n is the bits per pixel. So, the overall data file size is given by n into m into small n bits. So, this is a few examples of digital image. The first one is a very famous image, Lina. This is the capacity of 512 into 512 pixels. The next two images is the size of 2048 and 2060. If the resolution is increases, the accuracy of the images is also increases. So, we will move into the digital image processing. Here, we have to concentrate two major tasks. The first one is the improvement of pictorial information for human understanding. The second point is the processing of image data for storage, transmission, and representation. These are the main two tasks in digital image processing. In imaging science, the image processing is the processing of images using the mathematical operation. That is the simple definition for processing, where the input is a digital image, output may be either an image or the parameters related to the image. Now, we will move into the mathematical operations related with the image processing. First, let us move into the image enhancement. It highlights certain features of the image, such as the changing brightness or contrast, etc. The next one is the image restoration. It deals with improving the appearance of an image based on the mathematical models of image degradation. The next one is the color image processing. It includes the color modeling and the processing in the digital domain. The next algorithm is the wavelet and multi-resolution processing. It represents images in various degrees of resolution. The next algorithm is the image compression. It deals with the techniques for reducing the storage capacity of the image or the bandwidth to transmit it. The next algorithm is the morphological processing. It deals with the tools for extracting image components that are useful in the representation and description of the shape. The next, the mathematical operation is the segmentation. It is the process of partitioning an image into its constituent parts or objects. The next, the mathematical operation is the representation and description. It deals with the extracting the attributes that result in some quantitative information of the image. The final mathematical operation is object recognition. It is the process that assigns the label to the image, like car, bus, like that. Now we will move into the applications of digital image processing. Here I am list out few applications. The first one is medical applications, then defense, it is used in defense, also meteorology, environmental science, then manufacturing industry and crime investigation. Let us discuss one by one. First we move into the applications in medicine. Here the first image is a CT image, the second image is a PET image, the third image is a fusion of both CT and PET image, where the arrow mark indicates the metastatic lesions. In CT it provides the anatomic imaging, while in PET it is for nuclear imaging. To extract the exact localization of the metabolic abnormalities, the only possibility is we have to fuse both CT and PET image, that is abnormalities we have to find out with the help of the combination of PET and CT image. So normally the CT and MRI are important for surgical purpose, but the PET image has the higher detection rate for malignant tumors. The next application is meteorology. This is a satellite image. It is used to find out to locate the weather observation and prediction. The next one is applications in environmental science. These are the various satellite images taken from the space. It is used for the purpose of monitoring environmental conditions on the planet, such as the pollution and the soil condition. The next application is in manufacturing industry. Here we have to find out the automated visual inspection of manufactured goods. The inspection for missing parts and detection of abnormalities is found out by the image processing. Here the first one is the printed circuit board. Here we have to find out the missing components. Here this is a tablet filling image. Here it is used to find out the filled tablets. Also this image is referred the bottle filling mechanism. It is used to fill the level of the liquid. Here this application is mainly for crime investigation. Here the original image is a fingerprint on a knife. This is the original image. It has a fingerprint on a knife. Then this image is enhanced to get the exact image. Also it is used, it is very easy to compare with the database. So that's all about the applications of digital image processing. Now let us move into the mathematical operations related with medical image processing with one simple example, that is a single brain image. First, this is a picture for image compression. It will reduce the size of the image. The second one is the image with noise reduction. The third one is the image with edge extraction. The next one is the image enhancement. It will enhance the image. The next one is the segmentation image. It will partition the image. The next output is thresholding of the given brain image. The next one is morphological operation. This is erosion operation. The next one is dilation operation, and the last one is image restoration. So these are the examples for the mathematical operation which is used in medical processing applications. Now we'll move into the medical imaging. The medical imaging is a routine and essential part of medicine. The pathologist can be observed directly rather than concluded from the symptoms. For example, a doctor can non-invasively monitor the healing of damaged tissue or the growth of a brain tumor and determine an appropriate medical response. That is an important feature of this medical imaging. Now let us move into the imaging modalities. What is meant by imaging modalities? The many different imaging techniques have been developed and are in clinical use because they are based on the different physical principles and techniques. So normally we have the different imaging techniques are called modalities. Normally we have two types of modalities. The first one is anatomical modalities. The second one is functional modalities. First, we look into the anatomical modalities. It provides insight into the anatomical morphology. They include the radiography, ultrasonography or ultrasound, the computed tomography, magnetic resonance imaging called MRI. The next one is functional modalities. It describes the metabolism activity underlying tissues or organs. It includes a single photon emission computed tomography is called SPECT image. The next one is positron emission tomography is called the PET image. The last one is functional MRI, the functional magnetic resonance imaging. All images are now acquired digitally and integrated in a computer based picture archiving and communication system is called PCS. Now we will move into the anatomical modalities. That is, this MRI image comes under anatomical modalities. Now we will move into the in-depth concept of MRI. It is a imaging technique that produces images of internal physical and chemical characteristics of an object from externally measured nuclear magnetic resonance signals, that is called NMR signal. This technique was independently discovered by Bloch and his co-workers at Stanford and Brussels and his colleagues at Harvard in 1946. The Bloch and Brussels shared this Nobel Prize in Physics for the discovery in 1952. Now let us move into the short outline of MRI. First, put the subject in a big magnetic field where the subject is a human body. Then now transmit the radio waves into the subject in the period of 2 to 10 milliseconds. Then turn off the radio waves transmitter. Now receive the radio wave retransmitted by the subject, that is by the human body. Now finally convert the measured RF data into the image. The final image is called MRI image. Now we will move to the in-depth operation of the MRI. First let us move into the principle of the MRI. Normally the composition of the human body is fat and water. That is the 63% of human body is hydrogen atom. Essentially all MRI is hydrogen imaging. Also the hydrogen is a single proton. Hydrogen atom proton possess the properties called spin. The spin is a small magnetic field will cause the nucleus to produce an NMR signal. Now this is the concept of the single proton. There is an electric charge on the surface of the proton, thus creating a small current loop. It's called magnetic moment mu. Also it has the mass which generates the angular moment J when it is spinning. Now, in the absence of the external magnetic field, the spins are oriented randomly due to thermal random motion. When a human body is placed in a large magnetic field, many of the free hydrogen nuclei align themselves with the direction of the magnetic field V0. So this behavior is called Larmor precision. The frequency of the Larmor precision is proportional to the applied magnetic field as defined by the Larmor frequency. Omega equal to gamma into B0, where gamma is the diamagnetic ratio, is a known constant for each type of atom. For hydrogen atom, the constant value is 42.58 MHz per Tesla, and B0 is field strength of applied magnetic field. Now let us move into the operation of MRI. To obtain an MRI image of an object, the object is placed in a uniform magnetic field V0 of the value between 0.5 to 1.5 Tesla. As a result, the object's hydrogen nuclei aligns with the magnetic field and create a net magnetic moment M parallel to the B naught. This behavior is illustrated in the next slide. Here, in the absence of the strong magnetic field, the hydrogen nuclei are randomly aligned as shown in figure A. Here, the hydrogen atoms are randomly placed. When the strong magnetic field B naught is applied, the hydrogen nuclei proceeds about the direction of the field as shown in figure B. Next, now we have to apply the radio frequency pulse, that is RF pulse, BRF, perpendicular to B naught. This pulse with a frequency equal to the Lorentz frequency causes the magnetic moment M to tilt away from B naught as shown in figure 2A, that is this picture. That is, the RF pulse causes the net magnetic moment of the nuclei to tilt away from the B naught as shown in figure B naught. Once the RF signal is removed, the nuclei realign themselves such that the net magnetic moment M is again parallel with the B naught. So, this return to equilibrium is referred to as the relaxation. During relaxation, the nuclei lose energy by emitting their own RF signal as shown in the figure. That is, once again it will come to the original position. At that time, it will emit the energy. This circle is referred to the emitted energy. This signal emitted is referred as FID, that is free induction decay response signal. The FID response signal is measured by the conductive field coil placed around the object being imaged. This measurement is processed and reconstructed to obtain the 3D MR image. That's the concept of getting the MRI image. Now, the intensity of a given tissue type depends on the proton density of the tissue. If the higher the proton density, the stronger the FID response signal. The contrast of the MRI image is also depends on two other important tissue-specific parameters. The first one is called the longitudinal relaxation time T1 and the transverse relaxation time T2, where the T1 is the time required for the magnetic moment to return to equilibrium. The T2 is the time required for the free induction decay response signal to falling off. When the MR images are occurred, the RF pulse BRF is repeated at a predetermined rate. So the period of RF pulse sequence is repetition time TR. Also, the FID response signal can be measured at various times within the TR interval. So the time between the RF pulse applied and the response signal is the echo time delay, is called TE. By adjusting the time between TR and TE, the accurate MR image can be made to contrast different tissue types. So this diagram describes the concept of TR and TE. The time delay between two consecutive RF signals is called a repetition time. The time delay between the RF signal and the response signal is called the TE. These are the response signal, these are the RF signals. Now, the MR image contrast is based on T2 weighted and T1 weighted. In T2 weighted image, if the duration of T2 is short means that is a low intensity signal. If the duration of the T2 is long means that is a high intensity signal. In same manner, in T1 weighted image, if the T1 is short means the high density image. If T2 is long means that is low density image. Then the most brain pathology has long T2 and long T1. So this is example brain image. where the TR and TE are adjusted such that the tissues with the high proton density appear bright in the first image, where the high proton density will appear in high intensity, then and the tissues with a long T2 appear bright in the second image. This is the concept of MRI, proton density weighted image and the weighted slice image. Now we will move to the final stage, that is advantage of digital processing for medical applications. The first and important application is the digital data will not change when it is reproduced any number of times and retains the originality of the data. Also, the displaying images immediately after occurring is very important. Suppose if we are going for analog processing, just we have to process it to display, before display. Then the next point is enhancement of images to make them easier to the physician to interpret. Then the next point is quantifying changes over time. Then providing a set of images for teaching to demonstrate examples of disease or features in any image for the student community. The final application is the quick comparison of the image. Just we have to compare two images and we have to find out the attributes very easily. Now we will come to the conclusion, that is the summary of the lecture. So far we have discussed about the introduction of digital image processing, then we will discuss the few applications of digital image processing, then discuss the concept of medical imaging, the definition, what is medical imaging and all. Then we will move into the imaging modalities. The imaging modalities, normally we have two types of imaging modalities. The first one is the anatomical modalities, the next one is the functional modalities. Then we have discussed about the principle and operation of the magnetic resonance imaging. Then finally we discussed the advantage of digital processing for medical applications. That's all about the lecture.